So, focusing on these problems and how to combine exponential expressions, in other words, a power of x with another power of x, what we're always interested in doing is translating the arithmetic that's happening to the powers into arithmetic that happens instead to the exponents. So the question is always, what happens to the exponents when we carry out one of these operations? So let's start with the first example, x to the third times x to the fourth. What do you end up doing with those exponents to simplify this into a single factor? Add them. So how do you know what in this example is telling you that addition of these exponents is the appropriate operation? How do you know adding is the right thing? What are we doing to the powers that indicates we should be adding the exponents? Multiplying, right. So this is all about the relationship between those two operations, the operation of multiplication, which is happening kind of on the ground floor to these various expressions, right? The x to the third and the x to the fourth are kind of here on the ground level being multiplied. But then taking that operation and kind of raising it up into the exponent. When that happens, it changes its stripes. From what used to be multiplication, now becomes addition. And multiplication and addition are related operations, one to another, right? Specifically, if we think about arithmetic, multiplication is really defined as a process of repeated addition. Right? Multiplying something by 5 is the same as adding it to itself 5 times. And so there's this intimate relationship between those two operations that helps to explain why this exponent property works the way that it does. And so I like to kind of illustrate that by saying on this diagram, if what I'm doing to powers is multiplication, then what I end up doing to the exponents is the operation that's directly below it. So if I move the operation up, then the type of operation moves down a step. If I multiply powers, I end up adding their exponents. But then that same relationship also exists between all of the other operations that are in this little layer cake diagram of arithmetic. If when I multiply powers, I end up adding exponents, then I know that, for example, in our second problem here, x to the third times x to the fourth divided by x to the ninth, if I simplify what's in the numerator, then you've already told me that what's up there is x to the seventh. But now, according to this diagram, what should I do now that I'm dividing the power x to the seventh by x to the ninth? What do I do to their exponents to simplify that expression? Subtraction, right. If when I multiply powers I add exponents, then when I do the opposite of multiplication, division, to powers, I should do the opposite of addition, subtraction, to their exponents. Right? So, x to the seventh divided by x to the ninth is really x to the 7 minus 9. What's 7 minus 9? Negative 2. So one way of writing our final answer here would be to write it as x to the minus 2. But for a variety of historical reasons, I suppose, we don't like leaving answers in that kind of fashion. We don't like leaving answers that have negative numbers in the exponent. One of the reasons for which is that it's not a very transparent way to write this. It's not really clear. We know that raising something to the power 2 means multiply it by itself like twice, right? But it's not really possible to multiply something by itself negative 2 times. So is there a way that we can rewrite that to make it more obvious what's happening when we raise a power, when we raise a quantity to a negative 2 power? What can I do to this to make that exponent positive instead of negative? Turn it into a fraction. Great. So what I'll do is, how do you generally turn a number into a fraction, a whole number into a fraction? What can you do? Yeah, just put a 1 under it. So I'll start by putting a 1 under it. That turns it into a fraction with a denominator. And now that I've turned it into a fraction, what can I do to make that negative exponent positive? What's the trade-off? Gabby?
You write its reciprocal of 1 over x to the second.
Right. So to turn a negative exponent positive, you trade multiplication for division. looking at our layer cake diagram, to turn an exponent from negative to positive is moving kind of from right to left on this layer cake, right? Trade this operation for its opposite in the exponent. But then, because of the linkage between these two rows, that's the same thing as turning division of the power into multiplication, or vice versa. And in practice, what that looks like is taking the power and moving it either from the numerator to the denominator, or from the denominator to the numerator. Just change its position within the fraction to turn its exponent from negative to positive, or vice versa. So, all of that is a somewhat long-winded way to say that what we really want to do is just move that power down into the denominator. And what used to be x to the negative 2 upstairs becomes x to the positive 2 downstairs. And I suppose we still have that 1. What am I going to have here in the now empty numerator? Yeah. Because what we've really done is we've really kind of multiplied the numerator and denominator by x squared here to accomplish this moving from top to bottom. And if I multiply x to the minus 2 by x to the positive 2, I end up with no powers of x at all. What I end up with is x to the power 0, and x to the power 0 is the same as 1. So if we wanted to, we could declutter this by getting rid of the 1 in the denominator and writing our final answer as 1 over x squared. This little move we did here at the end to turn the negative exponents positive is something that I know Alex will always expect you to do. I think the wording of the problems when they show up on the exams and quizzes will also explicitly request that you always write your answers using only positive exponents. So this is a step not to be forgotten and not to be underestimated either, because there are a number of ways that it could be screwed up as well. Just remember at the end of the problem. So I like to wait till the very end of a problem to do this. But in order to do it, just flip-flop, either from numerator to denominator or vice versa. Other questions about this middle example that you'd like to hear more about before we look at the last one? So the first and second example involved only a multiplication of powers and a division of powers. Our third example also involves the raising of a power to another power. So that's one new thing that we're going to have to contend with. It also, furthermore, has this parentheses thing going on, right? We're grouping together x to the third times x to the fourth, and then we're raising that whole quantity to a power. So how did you approach this one? So one safe way of approaching this problem is to follow the order of operations. We are simplifying an expression after all, and simplification involves following the order of operations. Order of operations would tell us, look inside the parentheses first, which Brian did, and said, well, the first thing I'm doing is x to the third times x to the fourth, which we know now to be what?
7.
X to the seventh. Because multiplying powers is the same thing as adding their exponents, again, if the base is the same, if they're both powers of the same quantity. And so when that dust settles, we end up with x to the seventh, and then in parentheses, squared, divided by x to the ninth. So far that's a familiar step. The next step is one we haven't talked about yet. Now that we've satisfied the p in the order of operations, what comes afterwards? Exponents, the e in the order of operations. So we have to figure out now, when I raise a power to a power, what happens to those exponents? What are we going to do with the 7 and the 2? Multiply. How do you know that it's multiply? The 2's on the outside of the parentheses. We're raising a power to a power. Another way to think about it is just to take our understanding of powers and exponents that we had from before and just move it up one level on the layer cake over here. Right? Because exponentiation, raising something to a power, is the same thing as repeatedly multiplying it by itself. That means that exponentiation has the same relationship to multiplication that multiplication had to addition, which is why exponentiation belongs on this layer of the layer cake that's on top of multiplication. And according to our overall philosophy, whatever happens to the powers, we just need to move down one step on the layer cake to figure out what happens to their exponents. So if I raise a power to a power, then I should multiply the exponents together to simplify. So x to the 7, the quantity squared, is better known as x to the 7 times 2 or x to the 14. So again, power of a power. And having parentheses is also a pretty good way of kind of the power of a power jumping out at you, as Brian was saying. You can't really take a power of a power and write it very efficiently without using parentheses around the inside power. So those powers get multiplied, those exponents, get multiplied, and leave us with x to the 14. And then how do we finish simplifying this expression? Right, because I'm dividing powers of x, their exponents, subtract, and I end up with x to the power of 14 minus 9, which is x to the power 5. And that's that. So probably the most important skill to get well practiced at for the whole first phase of Module 6 is the skill of converting arithmetic operations done to powers into arithmetic operations done instead to their exponents. Multiplying powers means adding their exponents. Dividing powers means subtracting their exponents. And raising a power to a power involves multiplying exponents. There's one more on here that we haven't talked about now, but we will when we get to Module 10. That's this connection right here between taking a radical and dividing exponents. But that's something we won't have to worry about until April. So for now, we'll just leave that one be.